Mars sits roughly 225 million kilometers away. With current rockets, astronauts could reach it in about 7 months. Alpha Centauri, the nearest star system beyond our Sun, sits 4.37 light-years away. At the same speed that carried Voyager 1 out of the solar system, reaching Alpha Centauri would take over 70,000 years. That is not a typo. The closest star demands a journey 100,000 times longer than reaching Mars. We talk about both destinations as if they belong on the same cosmic to-do list. They do not. The gap between planetary travel and interstellar travel is not a gap at all. It is a wall built from the most unforgiving numbers in physics, and those numbers are about to shatter everything you thought you knew about space travel. If you enjoy journeys that change how you see the universe, hit that like button and subscribe. It truly helps the channel grow. Now, let's begin. On July 20th, 1969, 3 human beings climbed into a capsule roughly the size of a large car and left Earth. The Saturn V rocket that carried them weighed roughly 6.2 million pounds at launch. It burned through 2,000 tons of propellant in under 3 minutes, and it pushed the Apollo 11 crew to a speed of roughly 25,000 miles per hour, fast enough to escape Earth's gravity and coast toward the Moon. That journey covered approximately 240,000 miles. The crew reached lunar orbit in about 3 days. From launch to landing on the Sea of Tranquility, the entire outbound trip lasted less than 4 days. Humanity's first voyage to another world was shorter than a long weekend. Now consider where we stand more than half a century later. SpaceX has built and tested the largest rocket in human history. NASA has launched the Artemis program, with the explicit goal of returning astronauts to the Moon as a proving ground for deeper missions. Private companies and national space agencies on 4 continents have publicly stated their intention to send humans to Mars. The rhetoric is confident, the timelines are ambitious. Some projections place the first crewed Mars mission within the next 10 to 15 years. This confidence is not delusional. Mars is genuinely within technological reach. But understanding why requires grappling with the specific numbers that define the journey, not the inspirational rhetoric, not the cinematic trailers, the actual physics. Mars orbits the Sun at an average distance of approximately 228 million kilometers from Earth. But because both planets move along elliptical orbits at different speeds, the actual distance between them changes constantly. At their closest approach, called opposition, Mars can come within roughly 55 million kilometers of Earth. At their farthest separation, when the Sun sits between them, the distance stretches to over 400 million kilometers. The geometry of 2 planets chasing each other around the same star on different tracks at different speeds means that the Earth-Mars distance is never fixed. It oscillates in a cycle that repeats roughly every 26 months. Space agencies do not aim for the closest approach. They aim for energy efficiency. The standard route to Mars is called a Hohmann transfer orbit, an elliptical path that uses the least possible fuel to move a spacecraft from Earth's orbit to Mars's orbit. This trajectory was mathematically described by Walter Hohmann in 1925, and it remains the foundation of every Mars mission ever flown. The beauty of the Hohmann transfer is its elegance. The spacecraft fires its engines once to leave Earth orbit, coasts along a curved path that intersects Mars's orbit at precisely the right moment, and then fires again to slow down and be captured by Martian gravity. 2 burns, 1 long coast, months of patience. A Hohmann transfer to Mars takes approximately 7 months. Some mission architectures extend this to 8 or 9 months, depending on the specific planetary alignment and the spacecraft's mass. The launch windows for this trajectory open roughly every 26 months, when Earth and Mars align favorably. Miss the window, and you wait more than 2 years for the next one. This constraint alone shapes entire mission architectures. Every component, every system, every supply chain must synchronize to meet a calendar set not by engineers, but by orbital mechanics. 7 months might sound like a long trip, It is, but consider what it means in terms of speed. A spacecraft on a Hohmann transfer to Mars travels at roughly 24 kilometers per second relative to the Sun at departure. That translates to about 86,000 kilometers per hour. Fast by any earthly standard. A commercial airliner cruises at roughly 900 kilometers per hour. The International Space Station orbits Earth at about 28,000 kilometers per hour. A spacecraft departing for Mars travels 3 times faster than anything in low Earth orbit. But in cosmic terms, it is a crawl. The spacecraft coasts for most of the journey, carried by orbital mechanics rather than continuous thrust. The rocket does the hard work at the beginning, pushing the vehicle onto the right trajectory and again at the end, slowing it down to enter Martian orbit or begin atmospheric entry. The energy required for this maneuver is measured in a concept called delta V. Delta V represents the total change in velocity a spacecraft must achieve to complete a mission. It is the universal currency of spaceflight. Every maneuver, every orbit change, every landing and liftoff costs delta V, and every kilogram of propellant you carry to produce that delta V adds mass, which itself demands more propellant, creating a compounding problem that has defined rocket engineering since the discipline began. For a one-way trip from low Earth orbit to the surface of Mars, the total delta V budget is approximately 5.7 kilometers per second. That includes the trans-Mars injection burn, the course correction maneuvers during cruise, the Mars orbital insertion burn, and the descent to the surface. For context, the delta V required just to reach low Earth orbit from the launch pad is roughly 9.4 kilometers per second. Getting off Earth is actually harder, in energy terms, than getting from Earth orbit to Mars. This is a remarkable fact that reveals something important about the solar system. Once you have escaped the deep gravity well of Earth's surface, the rest of the inner solar system becomes surprisingly accessible. 5.7 kilometers per second is significant. It demands powerful rockets and large quantities of propellant, but it is not beyond our engineering capability. The Saturn V that carried Apollo astronauts to the Moon could generate far more delta V than this Mars requirement. The challenge with Mars is not raw power. It is sustaining human life for 7 months in deep space, landing safely on a planet with a thin atmosphere, and ideally getting the crew back home. SpaceX's Starship represents the closest thing to a near-term Mars vehicle. Standing approximately 120 meters tall when mated to its super-heavy booster, Starship is designed to carry over 100 tons of payload to low Earth orbit. Its 33 Raptor engines on the booster stage alone generate roughly 74 meganewtons of thrust at liftoff, making it the most powerful launch vehicle ever constructed. The Raptor engines burn liquid methane and liquid oxygen, a propellant combination chosen specifically because methane can theoretically be manufactured on Mars using the Sabatier reaction, which combines atmospheric carbon dioxide with hydrogen to produce methane and water. This in-situ resource utilization could enable return trips without carrying all the fuel from Earth, a concept that fundamentally changes the mass budget of a Mars mission. Consider what in-situ refueling means in practical terms. Without it, a crewed Mars mission must carry all the propellant for the return journey from Earth. That means launching enormous quantities of fuel into orbit, transferring it to the Mars vehicle, hauling it across interplanetary space, burning some of it to land on Mars, and then burning the rest to launch back into Martian orbit and return home. The mass penalty is crushing. With in-situ refueling, the return propellant is manufactured on the Martian surface using local resources. The outbound spacecraft arrives lighter. The mission becomes cheaper. The architecture becomes feasible rather than aspirational. SpaceX has projected that a fully refueled Starship in low Earth orbit could reach Mars in as little as 6 months, using a standard Hohmann-like transfer. More aggressive trajectory options using additional propellant to shorten the coast phase could potentially reduce transit time to 4 or 5 months. These faster trajectories require more fuel, which means more orbital refueling launches, but they remain within the boundaries of chemical propulsion physics. Nothing about these projections requires new science. They require new hardware, new operational experience, and new levels of reliability. But the physics is settled. NASA's approach is more conservative but follows the same fundamental principles. The Artemis program uses the Space Launch System rocket and the Orion capsule to establish a crewed presence on and around the Moon. This lunar infrastructure serves as a test bed for the technologies needed for Mars, including life support systems, deep space habitation modules, and orbital refueling techniques. The Moon sits roughly 3 days away from Earth. If something goes wrong, the crew can return relatively quickly. Mars offers no such safety net. A crew on Mars must wait for the next launch window, roughly 26 months, before they can come home. This means the life support systems must work flawlessly for over 2 years. The habitat must protect its occupants for over 2 years. The medical facilities must handle emergencies for over 2 years. Proving these systems at the Moon first is not timidity, it is prudence. NASA's current Mars architecture envisions a transit vehicle assembled in lunar orbit that would carry astronauts to Mars on a mission lasting approximately 2 to 3 years round trip, including surface time. The design calls for advanced propulsion, possibly nuclear thermal engines that could cut the transit time significantly, and a deep space habitat module that serves as home for the crew during the long coast phases. Every component of this architecture exists in some stage of development. None of it requires physics that has not been demonstrated. The energy numbers behind these missions are large but finite. Launching a crewed Mars mission requires putting roughly 1,000 tons of hardware and propellant into low Earth orbit. At current launch costs, this represents tens of billions of dollars. But the cost is economic, not physical. There is no law of nature that prevents us from assembling this hardware in orbit. There is no unsolved physics equation blocking the trajectory. There is no material science barrier that makes the heat shield impossible or the life support system unachievable. The barriers are money, political will, and the slow accumulation of engineering experience. These barriers are real. They are formidable, but they are human barriers, not natural ones. Mars is an engineering problem. It demands better rockets, better life support, better landing systems. All of these challenges are solvable with sufficient funding and development time. The physics works. The chemistry works. The orbital mechanics are well understood. Every robotic mission humanity has sent to Mars, from the Viking landers in 1976 to the Perseverance rover currently driving across Jezero crater, has confirmed that the journey is achievable with existing or near-term technology. Consider the roster of spacecraft that have already made the trip. Mars Pathfinder in 1997, the Spirit and Opportunity rovers in 2004, Curiosity in 2012, the InSight lander in 2018, Perseverance and the Ingenuity helicopter in 2021, China's Zhurong rover, which landed successfully in 2021, demonstrated that multiple nations can independently execute Mars surface missions. India's Mangalyaan orbiter, launched on a shoestring budget in 2013, reached Mars orbit on its first attempt. The United Arab Emirates placed its Hope orbiter around Mars in 2021. Mars is not the exclusive domain of superpowers. It is increasingly accessible to any nation with disciplined engineering and modest resources. Each of these missions traveled the same approximately 300 million kilometer trajectory that a crewed mission would follow. Each one survived the 7-month cruise, executed a precision entry into Mars's atmosphere, and either landed successfully on the surface or inserted into stable orbit. The technology that carried these robotic explorers is fundamentally the same technology that would carry human beings. Bigger, heavier, more complex, but the same category of machine. The Mars entry sequence alone illustrates how far our engineering has come. A spacecraft arriving at Mars hits the atmosphere at approximately 20,000 kilometers per hour. In roughly 7 minutes, it must decelerate to zero and land softly on the surface. This process, sometimes called the 7 minutes of terror, involves a heat shield, a supersonic parachute, retro rockets, and in the case of Curiosity and Perseverance, a hovering sky crane that lowers the rover on cables to the surface below. Every one of these steps works. Every one has been successfully demonstrated in the unforgiving environment of another planet's atmosphere. The sky crane deserves particular attention because it represents the kind of audacious engineering that makes Mars achievable. A rocket-powered platform hovers above the Martian surface while lowering a 1-ton rover on nylon cables. When the rover's wheels touch ground, explosive bolts sever the cables and the sky crane flies away to crash at a safe distance. This sounds like something designed by a science fiction writer with no regard for practicality. Yet it has worked flawlessly twice, on 2 separate planets' worth of landings, delivering both Curiosity and Perseverance to precisely targeted locations on the Martian surface. None of this is easy. Mars missions fail. The European Space Agency's Schiaparelli lander crashed in 2016 when its computer misinterpreted sensor data during descent. Russia's Mars 96 mission never left Earth orbit. Japan's Nozomi orbiter missed Mars entirely. Britain's Beagle 2 lander reached the surface, but failed to fully deploy its solar panels and was never heard from again. The success rate for Mars missions sits at roughly 50% historically, though it has improved dramatically in recent decades as technology has matured and mission teams have accumulated hard-won experience. But failure at Mars is engineering failure. Sensors malfunction. Software contains bugs. Parachutes deploy late. Communication links drop at critical moments. These are problems that better testing, better design, better quality control, and more experience can fix. They are the same category of problems that plagued early aviation, early submarine development, early bridge construction. They are not problems that require new physics. They require new competence. This distinction matters enormously for what comes next. Mars is the hardest thing humanity has ever seriously attempted in space, but it sits firmly within the domain of achievable technology. The energy requirements are high but manageable. The travel times are long but survivable. The distances are vast by human standards but tiny by cosmic ones. To put Mars in proper cosmic perspective, consider this. Light travels from Earth to Mars in approximately 12.5 minutes at closest approach. When Mars sits on the far side of the Sun, the light travel time stretches to about 22 minutes. A conversation with a Mars colony would involve delays of roughly 4 to 24 minutes each way depending on orbital positions. Annoying, certainly. You could not hold a phone call, but you could exchange messages with a rhythm resembling slow email. You could send a question and receive an answer within the same hour. Medical emergencies on Mars could be supported by real-time advice from Earth, delayed but not disconnected. Mission control could monitor telemetry and respond to anomalies within minutes rather than days. Compare this to the Moon, where light takes roughly 1.25 seconds to travel each way. Apollo astronauts experience barely perceptible communication delays. Mars multiplies that delay by a factor of roughly 600 to 1,000, significant, but not unbridgeable. The delay is an inconvenience, not a severance. The Apollo program demonstrated that humanity could send people to a destination roughly 1.25 light seconds away. Mars sits roughly 3 to 22 light minutes away. That is a significant increase, a factor of roughly 1,000 in distance compared to the Moon. But it is a linear increase, not an exponential one. The same physics that carried Apollo to the Moon, chemical propulsion and orbital mechanics, scales directly to the Mars problem. You need bigger rockets, more fuel, longer mission timelines, and better life support. You do not need fundamentally different physics. You do not need to break new ground in thermodynamics. You do not need to discover new particles or invent new materials that defy known science. This is the critical point that must be established before we look deeper into space. Mars stretches our current engineering to its limits, but those limits bend, they flex. They yield under sustained pressure from funding, from talent, from institutional commitment. Given enough money, enough political will, and enough time, Mars yields. The planet sits within the reach of chemical rockets, the same technology that powered every human spaceflight mission in history. It demands that we build bigger, plan better, and endure longer. But it does not demand that we reinvent the laws of thermodynamics. It does not demand breakthroughs in fundamental science. It demands only that we do what engineers have always done: take known physics and push it further, faster, and more reliably than before. Mars is the finish line we can see from where we stand. The track is long, the race is grueling. The obstacles are real, and some of them will claim missions and possibly lives before we succeed. But the physics allows the race to be run with the legs we already have. Every required technology either exists today or is under active development. The propulsion works, the navigation works. The landing systems work. The life support will work once it has been tested and refined in the lunar environment. The timeline is measured in years and decades, not centuries and millennia. This is what makes Mars the essential baseline for understanding what comes next. Mars is hard, Mars is expensive, Mars is dangerous. But Mars is possible, demonstrably, quantifiably, physically possible. We have sent dozens of robots there. We have driven vehicles across its surface. We have flown a helicopter in its atmosphere. We have mapped its terrain to centimetre-level precision from orbit. The planet is known to us. Its challenges are catalogued. Its risks are understood. Its rewards, both scientific and civilizational, are beyond calculation. Everything changes when you look past Mars. Everything changes when you aim for the stars. The track does not merely get longer. It does not simply demand more fuel or more patience. The track transforms into something fundamentally, categorically, mathematically different from anything we have ever attempted or are currently capable of attempting. The numbers undergo a shift so violent that the very meaning of the word far changes beneath your feet, and the first star on that impossible track has a name that sounds deceptively close. A name that sits in every astronomy textbook as the nearest stellar neighbour. A name that implies neighbourliness, proximity, accessibility. Alpha Centauri. Alpha Centauri is not one star. It is a system of three. Alpha Centauri A and Alpha Centauri B form a binary pair, two sun-like stars locked in a gravitational embrace, orbiting each other every roughly 80 years. Alpha Centauri A is slightly larger and brighter than our Sun, a G-type main sequence star burning with a yellowish-white luminosity, roughly 1.5 times solar output. Alpha Centauri B is slightly smaller and dimmer, a K-type orange dwarf radiating about half the Sun's energy. Together they form a double star system visible to the naked eye from the southern hemisphere, appearing as a single brilliant point of light in the constellation Centaurus, the third brightest star in Earth's sky after Sirius and Canopus. A third, much smaller star called Proxima Centauri orbits this pair at a vast distance, roughly 13,000 astronomical units away, taking over 500,000 years to complete a single orbit. Proxima Centauri is a red dwarf, dim and cool by stellar standards, invisible without a telescope despite being closer to Earth than any other star. Yet it holds a distinction that no other star in the universe can claim. It is the closest individual star to our Sun, sitting approximately 4.24 light-years away. The binary pair sits slightly farther, at about 4.37 light-years. In 2016, astronomers confirmed the existence of a planet orbiting Proxima Centauri within its habitable zone. Proxima Centauri b, as it was designated, has a minimum mass roughly 1.2 times that of Earth. Its discovery electrified the scientific community and the public imagination. The nearest star to our Sun hosts a roughly Earth-sized world in an orbit where liquid water could theoretically exist. Headlines declared we had found our nearest potentially habitable neighbour. The implication was tantalising. If humanity ever reaches for the stars, This planet orbiting this star would be the logical first destination. These numbers sound modest, 4.24 light-years. Astronomy textbooks cite this distance casually, almost parenthetically, as if it were the next bus stop past Mars. Popular science articles mention Alpha Centauri as our nearest stellar neighbour, with a tone that implies accessibility, as though proximity in cosmic terms translates to proximity in human terms. It does not remotely. Converting that distance into units humans can grasp reveals a chasm so vast it redefines the word far. It does not merely stretch the concept, it breaks it entirely and forces you to build a new one from scratch. 1 light year equals approximately 9.46 trillion kilometers. That is the distance a beam of light, traveling at roughly 300,000 kilometers per second, covers in 1 calendar year. Light is the fastest thing in the universe. Nothing outruns it. Nothing matches it. In a single second, light crosses a distance that would take a commercial airliner roughly 12 hours to fly. In 8 minutes and 20 seconds, light covers the entire distance from the Sun to Earth, 150 million kilometers. And even traveling at this absolute cosmic speed limit, crossing a single light year requires 365 days of continuous, uninterrupted travel at the maximum velocity the universe permits. Now multiply that distance by 4.24. The distance to Proxima Centauri is roughly 40.1 trillion kilometers. Written out in full, that number stretches across the page. 40,100 billion kilometers, 40 trillion, a number with 13 digits. This number resists comprehension. The human brain evolved to process distances measured in footsteps, in horizons, in the space between villages. Our ancestors needed to judge whether a predator was close enough to be dangerous or a water source far enough to require planning. The longest distances that mattered for survival were perhaps a few hundred miles. A journey of 1,000 miles was once considered an extraordinary undertaking, the stuff of epic poetry and legend. 40 trillion kilometers exists so far beyond everyday experience that no metaphor fully captures it. The number becomes noise. The brain reads it, acknowledges it, processes the syllables, and then quietly discards it because it has no framework for holding something that large. The cognitive machinery simply was not built for this, but let us try to anchor it anyway. Let us force the number into shapes the mind can hold, even imperfectly. Start with Mars. The distance from Earth to Mars at closest approach is roughly 55 million kilometers. This is the number established in the previous section, the distance that defines our nearest serious interplanetary destination, the distance that chemical rockets can cross in 7 months, the distance that dozens of robotic spacecraft have already successfully traversed. Now place that distance next to the Alpha Centauri number. The distance to Proxima Centauri is approximately 40 trillion kilometers. Divide 40 trillion by 55 million. The answer is roughly 727,000. That means the distance to the nearest star is approximately 727,000 times farther than the distance to Mars at its closest. 727,000. Not 727, not 7,000. 727,000 times farther. Even using the average Earth-Mars distance of roughly 225 million kilometers, which accounts for the fact that Mars spends most of its orbit much farther away than its closest approach, the ratio remains staggering. Divide 40 trillion by 225 million. The nearest star is approximately 178,000 times farther than the average distance to Mars. Let that settle. Not twice as far, not 10 times as far, not 100 times as far, not even 1,000 times as far, 178,000 times as far. If reaching Mars is a walk to the mailbox at the end of your driveway, roughly 30 meters from your front door, then reaching Alpha Centauri is a walk of 5,340 kilometers. That is roughly the distance from New York City to the far coast of Scotland for a trip to the mailbox. That is the ratio. That is what 178,000 means when translated into something the legs understand, even if the mind cannot. These analogies strain under the weight of the actual numbers. No everyday comparison does justice to a factor of 178,000. Human experience provides no reference point for it. The farthest distance most people ever travel in their lives, perhaps the circumference of the Earth at roughly 40,000 kilometers, is still 1 billion times smaller than the gap to Alpha Centauri. The number simply overpowers every frame of reference the human mind can assemble. You cannot feel it. You can only calculate it and then sit with the discomfort of knowing the calculation is correct. Now translate that distance into travel time using a spacecraft that actually exists. Voyager 1, launched in 1977, is currently the fastest human-made object, leaving the solar system relative to the Sun, travelling at approximately 17 kilometers per second, or about 61,000 kilometers per hour. Voyager 1 was not designed to go to the stars. It was designed to fly past Jupiter and Saturn using gravitational slingshots from those massive planets to gain speed. After completing its planetary mission, it kept going. Nobody stopped it. Nobody could. It crossed the heliopause, the boundary where the solar wind gives way to the thin plasma of interstellar space, in 2012. As of now, Voyager 1 is roughly 24 billion kilometers from Earth. It has been travelling for nearly half a century, and it has covered less than 0.06% of the distance to Alpha Centauri, less than 1 part in 1,600. After almost 50 years of continuous flight at 61,000 kilometers per hour, Voyager has crossed a sliver of the interstellar gap so thin it barely registers on a percentage scale. This is our current interstellar benchmark. This is the yardstick against which all interstellar ambitions must be measured. At Voyager 1's speed, reaching Proxima Centauri would take approximately 73,000 years. 73,000 years. The number is worth pausing over because it exceeds every meaningful human timescale by orders of magnitude. 73,000 years ago, anatomically modern humans had not yet left Africa in significant numbers. The great migration that would eventually populate every continent on Earth was still in its earliest stages. Neanderthals still lived across Europe and Western Asia. The last ice age had not yet reached its maximum glacial extent. No language had been written down. No city had been built. No crop had been planted. No animal had been domesticated. The entire history of agriculture, civilization, writing, mathematics, philosophy, science, industry, and spaceflight fits inside the last 10,000 years. A Voyager speed mission to the nearest star would require a journey 7 times longer than all of recorded human history combined. 7 complete cycles of everything humanity has ever accomplished, laid end to end, would still fall short of the travel time. This is not a problem of patience. It is a problem of meaning. No spacecraft can be designed to function for 73,000 years. No known material holds its structural integrity across geological timescales. Metals corrode and fatigue. Plastics degrade under ultraviolet exposure and particle bombardment. Lubricants evaporate, seals crack. Electronics fail as cosmic radiation slowly flips bits, corrupts memory, and destroys semiconductor junctions 1 atom at a time. No computer survives 73 millennia of bombardment by the high-energy particles streaming through interstellar space. No power source generates electricity for 700 centuries. Voyager 1 itself runs on 3 radioisotope thermoelectric generators, powered by the decay of plutonium-238. Those generators lose roughly 4 watts of output per year as the plutonium decays. They will fall below the minimum power threshold needed to operate any scientific instrument by roughly 2025 or 2026. After less than 50 years of flight, Voyager will go silent. Its transmitter will die. Its instruments will shut down one by one. The spacecraft will continue drifting, a dead husk of aluminum and silicon, for eternity. Asking the same technology to function for 73,000 years is not engineering. It is fantasy dressed in arithmetic. It is a number that exists on paper and nowhere else. But perhaps Voyager is too slow a benchmark. After all, Voyager 1 was not designed for speed. It was designed for planetary flybys, and its current velocity is a byproduct of gravitational assists from Jupiter and Saturn rather than brute propulsive force. Modern spacecraft can go faster. NASA's Parker Solar Probe, launched in 2018, has reached speeds exceeding 190 kilometers per second during close passes of the Sun. It achieves this velocity by falling deep into the Sun's gravity well, converting gravitational potential energy into kinetic energy during each perihelion pass, skimming through the solar corona at distances closer to the Sun than any spacecraft has ever ventured. At its fastest, Parker Solar Probe moves at roughly 11 times the speed of Voyager 1, making it the fastest object humanity has ever built by a significant margin. At that speed, reaching Proxima Centauri would take roughly 6,700 years, an improvement by an order of magnitude over Voyager's 73,000. But 6,700 years ago, the Egyptian pyramids had not yet been built. Stonehenge did not exist. The Sumerian civilization, often called the cradle of writing, was only just beginning to scratch the earliest cuneiform symbols into wet clay tablets. The Bronze Age was dawning across Mesopotamia. Human beings had only recently figured out how to smelt copper ore into usable metal. A Parker Solar Probe speed journey to the nearest star would consume more time than the entirety of what we recognize as civilization. Every empire that has risen and fallen, from Sumer to Rome to the British Empire, every language that has been spoken and forgotten, every war fought and every peace forged, every cathedral built and every city demolished. All of it fits inside the travel time to Alpha Centauri at the fastest speed any human machine has ever achieved. What about even faster benchmarks from other missions? New Horizons, the probe that flew past Pluto and transmitted the first close-up images of that distant world, left Earth at roughly 16.26 kilometers per second, one of the fastest departure velocities ever recorded for a spacecraft heading into the outer solar system. The Juno probe reached roughly 73 kilometers per second during its approach to Jupiter, though that speed was largely gained from Jupiter's own immense gravity rather than from onboard propulsion. The Helios 2 solar probe, launched in 1976, reached about 70.22 kilometers per second during its closest solar approach. None of these speeds meaningfully alter the interstellar timeline. At New Horizons' departure speed, the journey to Alpha Centauri would require roughly 78,000 years. At Juno's peak speed, roughly 17,000 years. At Helios 2's speed, roughly 18,000 years. The numbers shuffle between millennia and tens of millennia, but they never descend into centuries, let alone decades. The journey still demands timescales that dwarf civilization itself. The problem becomes sharper when you stack the two destinations side by side in concrete terms. A Hohmann transfer to Mars takes roughly 7 months. The same chemical propulsion technology, applied to a Voyager-class trajectory aimed at Alpha Centauri, would require over 70,000 years. That ratio, 7 months to 70,000 years, encapsulates the entire central tension of this story. Convert both to the same unit. 7 months is roughly 0.58 years. 70,000 years divided by 0.58 years yields a factor of approximately 120,000. The interstellar trip is roughly 120,000 times longer than the interplanetary one, using the same category of propulsion technology. One destination is within reach, the other is not. And the gap between them is not a gentle slope that future technology will gradually flatten. It is a cliff, a vertical face of numbers, so steep that no incremental improvement in rocket efficiency can scale it. Let us compress the solar system to make this visceral. Imagine the Sun is a basketball sitting on the 50-yard line of a football field. At this scale, the Sun's diameter of roughly 1.4 million kilometers has been shrunk to about 24 centimeters. Earth, at this scale, is a tiny peppercorn orbiting about 26 yards away from the basketball. Mars is another peppercorn, slightly smaller, sitting roughly 40 yards from the basketball. The asteroid belt is a scattering of dust grains between 40 and 60 yards out. Jupiter is a cherry sitting about 135 yards from the Sun, roughly the distance from the 50-yard line to the far end of a parking lot beyond the stadium. Saturn, with its famous rings, sits about 250 yards away. Uranus is roughly 500 yards out. Neptune is close to 800 yards. Pluto, at the distant edge of the classical solar system, is a pinhead roughly half a mile from the basketball. Half a mile? That is the entire classical solar system in this model. Everything we have explored, every planet we have photographed in detail, every moon we have mapped, every asteroid we have visited, every comet we have chased. From the Sun to Pluto, everything fits inside a half-mile sphere surrounding a basketball on a football field. Now, where is Alpha Centauri at this scale? Another basketball sitting in a city, roughly 4,300 miles away. If your Sun basketball is in New York, Alpha Centauri is past London, somewhere deep in continental Europe, perhaps sitting in a park in Berlin or Prague. The entire solar system, that half-mile bubble containing every world humanity has ever reached, is a speck compared to the distance to the next basketball. You could line up roughly 17 million copies of our solar system, edge to edge, between our Sun and Alpha Centauri. 17 million repetitions of the space that contains every world we have ever known, every landscape we have ever photographed from orbit, every crater we have ever named. This is the scale shock. This is the number that separates interplanetary from interstellar. When people talk about Mars and Alpha Centauri in the same breath, when science fiction treats them as equally plausible destinations separated only by a few decades of technological progress, when futurists casually suggest humanity will become an interstellar species within a few centuries, they are glossing over a numerical reality that does not gloss. The distance from Earth to Mars is a puddle you can step across if you stretch. The distance from Earth to Alpha Centauri is the Pacific Ocean, and you are standing on the shore without a boat, without a harbour, without even a clear understanding of how a boat capable of crossing that ocean could be built. Speed alone cannot solve this problem. To cross the Alpha Centauri gap in a single human lifetime, say 50 years, a spacecraft would need to travel at roughly 8.6% of the speed of light. That is approximately 25,800 kilometers per second. For perspective, the fastest spacecraft humanity has ever built, the Parker Solar Probe at perihelion, reached about 190 kilometers per second. Closing the gap between 190 kilometers per second and 25,800 kilometers per second requires an increase in speed by a factor of roughly 136. That factor sounds manageable until you consider what that speed increase actually demands in terms of the one resource that truly matters. Speed is not the real barrier, energy is. And this is where the Alpha Centauri problem transitions from merely difficult to fundamentally different from anything humanity has ever confronted. Kinetic energy scales with the square of velocity. This is basic physics, taught in introductory mechanics courses worldwide. But its implications at interstellar scales are anything but basic. Double the speed and you quadruple the required energy. Triple the speed and you need 9 times the energy. Increase the speed by a factor of 10 and you need 100 times the energy. Increase the speed by a factor of 136 and you increase the energy requirement by a factor of roughly 18,500. The energy needed to accelerate a spacecraft to interstellar velocities is not merely larger than what Mars requires. It belongs to a different category of physics entirely. It is not a bigger version of the same problem. It is a new problem, one that operates under constraints no existing or planned technology can satisfy. There is a temptation here to treat this as a temporary limitation. Surely technology will improve. Surely future rockets will be faster. Surely what seems impossible today will be routine tomorrow. And there is historical precedent for this optimism. In 1900, powered flight did not exist. The Wright brothers had not yet built their flyer at Kitty Hawk. Most serious scientists and engineers believed heavier-than-air flight was impractical or impossible. Lord Kelvin himself reportedly declared it so. By 1969, just 66 years later, humans walked on the moon. Technology does advance, sometimes at breathtaking speed. The 20th century proved that barriers which seem permanent can shatter within a single lifetime, but the advance from the Wright Flyer to the Saturn V involves scaling up within the same physics. Chemical combustion drove both aircraft and rockets. Kerosene and air powered the Wright Flyer's engine. Kerosene and liquid oxygen powered the Saturn V's first stage. The fundamental energy source, breaking and forming chemical bonds, remained identical across 7 decades of development. The engineers who built the Saturn V did not need to discover new laws of nature. They needed to build bigger, more efficient, more reliable machines using principles that were already understood when the Wright brothers first lifted off the sand at Kill Devil Hills. The Wright brothers would have recognized the chemistry inside a Saturn V engine. They would not have recognized the scale, but the science was the same. The advance from Mars to Alpha Centauri does not work this way. It is not a matter of building a bigger chemical rocket. Chemical propulsion has a hard ceiling, set by the energy density of chemical bonds. The strongest chemical bond practically usable in rocketry, the hydrogen-oxygen reaction, releases a specific amount of energy per kilogram of propellant. That amount is fixed by quantum mechanics. No clever engineering can extract more energy than the chemistry contains. No amount of funding, no number of engineers, no quantity of political will, no duration of development time changes the energy density of a hydrogen-oxygen bond. It is a constant of nature, as immovable as the speed of light. Reaching even 1% of the speed of light with chemical propulsion would require a fuel mass so absurdly large that it surpasses the mass of the observable universe. This is not hyperbole crafted for dramatic effect. It is math. The Tsiolkovsky rocket equation, published in 1897 by the Russian mathematician Konstantin Tsiolkovsky, describes the relationship between a rocket's final velocity, its exhaust velocity, and its mass ratio. The mass ratio is the ratio of the rocket's total initial mass, including all fuel, to its final mass after the fuel has been expended. For chemical rockets with an exhaust velocity of roughly 4.5 kilometers per second, achieving even 1% of the speed of light, about 3,000 kilometers per second, would require a mass ratio of approximately e to the power of 667. That number deserves a moment of contemplation. E to the power of 667. The number e, the base of natural logarithms, raised to the 667th power, produces a figure with approximately 290 digits. For comparison, the estimated number of atoms in the entire observable universe is approximately 10 to the 80th power, a number with 81 digits. The fuel mass required for a chemical rocket to reach 1% of light speed exceeds the number of atoms in the observable universe by a factor so immense it cannot be expressed in any meaningful way. This is not a difficult engineering problem that more money or more time could solve. It is a physical impossibility, not a practical impossibility, not an economic impossibility. A physical impossibility, as absolute and non-negotiable as the impossibility of travelling faster than light itself. Mars does not trigger this impossibility. Mars requires a delta V of roughly 5.7 kilometers per second, well within chemical rocket capability. The mass ratio for a Mars transfer is roughly 4:1, meaning you need about 3 kilograms of propellant for every kilogram of payload and dry structure. Expensive and heavy, yes, but ordinary. Achievable. Demonstrated repeatedly by real hardware on real missions. Alpha Centauri, even at the most modest interstellar cruise speed, demands delta V values hundreds or thousands of times larger. At 1% of light speed, the delta V requirement is roughly 3,000 kilometers per second. At 10%, roughly 30,000. The rocket equation does not care about human ambition. It does not care about funding levels or political will or inspirational speeches or the dreams of science fiction writers. It cares about exhaust velocity and mass ratio. And for chemical rockets, the equation says no to the stars. Emphatically, mathematically, permanently no. This is the wall. Not a wall made of funding shortfalls or political indifference or bureaucratic timidity. A wall made of thermodynamics, conservation of energy, and the fundamental limits of chemical bond strength. Chemical bonds contain a fixed amount of energy. That energy, when released through combustion and directed through a rocket nozzle, produces a fixed exhaust velocity. That exhaust velocity, plugged into the Tsiolkovsky equation, produces a fixed relationship between fuel mass and achievable speed. And that relationship, followed to its logical conclusion at interstellar scales, produces mass ratios that exceed the mass of galaxies. The wall is not tall, it is infinite. The next logical question is whether better propulsion technologies can breach this wall. Humanity has not stood still at chemical rockets. Engineers and physicists have designed, tested, and theorized about propulsion systems far more capable than anything that burns hydrogen and oxygen. Nuclear thermal engines were built and successfully test-fired on the ground in the 1960s. Ion drives have propelled spacecraft across the asteroid belt. Solar sails have been deployed and demonstrated in Earth orbit. Theoretical studies have examined nuclear pulse propulsion, fusion engines, antimatter drives, and laser-pushed light sails. Each of these technologies offers higher exhaust velocities than chemical rockets. Each one climbs higher on the propulsion ladder, offering more delta-V per kilogram of fuel, more speed per unit of onboard mass. The question is whether any of them climb high enough. The question is whether any propulsion technology ever designed, tested, or seriously imagined transforms Alpha Centauri from physically impossible to merely very difficult. The question is whether the wall between planetary and stellar travel can be breached, or whether it stands as a permanent boundary marking the edge of what moving objects can achieve in this universe. The answer begins with nuclear fire, ascends through the most audacious engineering concepts ever committed to paper, and ends at the hardest wall in physics. Every propulsion system ever built or seriously designed by humanity can be placed on a ladder. The rungs of this ladder are ranked by a single number, a number that determines how far each technology can carry us and how fast it can get us there. That number is specific impulse, measured in seconds, and it describes how efficiently a rocket engine converts propellant mass into thrust. A higher specific impulse means more velocity change per kilogram of fuel expended. It means the engine wrings more motion out of every gram of propellant that passes through it. Specific impulse is the single most important metric in rocketry. It is the number that separates a technology capable of reaching Mars from a technology capable of reaching Alpha Centauri. And as we climb the ladder rung by rung, testing each technology against both destinations, a devastating pattern emerges. Every rung that works for Mars breaks the moment you point it toward the stars. Chemical rockets sit on the bottom rung. They are the workhorses of spaceflight, the only propulsion technology that has ever carried human beings off the surface of the Earth. Every crewed mission in history, from Yuri Gagarin's single orbit in 1961 to the most recent astronaut launches aboard SpaceX Crew Dragon, has relied on the controlled combustion of chemical propellants to generate thrust. The physics is straightforward. Mix a fuel with an oxidizer. Ignite the mixture inside a combustion chamber. The resulting hot gas expands and exits through a nozzle at high velocity. Newton's third law does the rest. The exhaust pushes backward. The rocket pushes forward. The Space Shuttle main engines, among the most sophisticated chemical rockets ever built, achieved a specific impulse of roughly 453 seconds in vacuum. SpaceX's Raptor engines, which power the Starship vehicle, reach approximately 350 seconds at sea level and higher in vacuum, the most efficient chemical rocket engine ever tested, burning liquid hydrogen and liquid oxygen in an expander cycle configuration, topped out at around 460 seconds. This ceiling is important. It is not set by engineering. It is not a consequence of imperfect nozzle design or suboptimal combustion chamber geometry. It is set by chemistry itself. The energy released when two hydrogen atoms bond with one oxygen atom to form a water molecule represents a fixed quantity determined by quantum mechanics. That energy, divided by the mass of the exhaust products, determines the maximum exhaust velocity. No clever engineering, no exotic fuel additive, no advanced manufacturing technique can push past this thermodynamic wall. 460 seconds is roughly where chemical propulsion maxes out. It is a hard limit written into the periodic table. At 450 seconds of specific impulse, chemical rockets work beautifully for Mars. The delta-V budget for a one-way Mars transfer from low Earth orbit is approximately 5.7 kilometers per second. At chemical level specific impulse, this requires a mass ratio of roughly 4:1. 3/4 of the vehicle's initial mass is propellant. 1/4 is payload, structure, engines, and everything else. Heavy, yes. Expensive, absolutely. But the ratio is manageable. Real rockets operate at these mass ratios routinely. The Saturn V that sent Apollo astronauts to the Moon had a mass ratio exceeding 20:1 for the entire stack, including reaching orbit. Chemical rockets have more than enough performance to handle the Mars problem. Every Mars mission ever launched, robotic or otherwise, used chemical propulsion. Every planned crewed Mars mission, whether from NASA or SpaceX or the China National Space Administration, intends to use chemical rockets for the primary propulsive maneuvers. The technology is mature, reliable, and adequate for interplanetary distances, but apply chemical rockets to the Alpha Centauri problem and the numbers disintegrate. The previous section established that reaching even 1% of light speed with chemical propulsion demands a mass ratio exceeding the mass of the observable universe. That conclusion was not rhetorical. It was a direct consequence of the Tsiolkovsky rocket equation, applied to an exhaust velocity of 4.5 kilometers per second and a target velocity of 3,000 kilometers per second. Chemical rockets cannot take us to the stars. This is not a funding problem or a political problem or a patience problem. It is a physics verdict handed down by thermodynamics. No amount of money changes the energy content of a chemical bond. So, we climb to the next rung. Nuclear thermal propulsion replaces chemical combustion with a nuclear fission reactor. Instead of burning fuel and oxidizer together, you pump a propellant, typically liquid hydrogen, through the core of a nuclear reactor operating at temperatures exceeding 2000 degrees Celsius. The hydrogen absorbs heat from the reactor, expands violently, and exits through a nozzle at much higher velocity than any chemical combustion reaction can produce. The propellant itself is not the energy source. The reactor is. This decoupling of energy source from propellant mass is what gives nuclear thermal its advantage. You are heating the lightest possible gas with the densest possible energy source, and the result is a significant jump in specific impulse. NASA tested this concept extensively in the 1960s and early 70s under the NERVA program, an acronym for Nuclear Engine for Rocket Vehicle Application. The program was not theoretical. Real hardware was built and fired at the Nuclear Rocket Development Station in the Nevada desert. NERVA engines ran for minutes at a time, producing thrust levels comparable to chemical upper stage engines, while achieving a specific impulse of approximately 850 seconds. Nearly double the best chemical rockets. The engines worked. They demonstrated the feasibility of nuclear thermal propulsion in ground-based test conditions. They were never flown in space because the program was cancelled in 1973, a casualty of post-Apollo budget cuts, shifting national priorities, and the political complexities of launching nuclear reactors through Earth's atmosphere. The cancellation was not a verdict on the technology's capability, it was a verdict on its political viability in that era. At 850 seconds of specific impulse, nuclear thermal propulsion transforms Mars missions. Transit time could potentially be reduced from 7 months to roughly 3.5 to 4 months, depending on the trajectory optimization. The improved fuel efficiency means less propellant mass in orbit, which translates directly to fewer refueling launches, lower mission costs, and greater payload capacity for scientific equipment and crew supplies. NASA is currently funding the development of nuclear thermal propulsion systems for future Mars missions through the DRACO program, a collaboration with the Defense Advanced Research Projects Agency. The agency recognizes that nuclear thermal represents a genuine step change for crewed deep space exploration within the solar system. But does nuclear thermal propulsion help with Alpha Centauri? The answer is devastating in its simplicity. Barely. Doubling the specific impulse from chemical levels sounds impressive in a Mars mission planning meeting. It sounds irrelevant in an interstellar context. The Alpha Centauri problem does not demand improvements measured in factors of 2. It demands improvements measured in factors of thousands. At 850 seconds of specific impulse, reaching 1% of light speed still requires a mass ratio of e to the power of roughly 350. That number still has more digits than atoms in a galaxy. The mass ratio has improved from physically impossible to slightly less physically impossible. The distinction is meaningless in practical terms. Nuclear thermal propulsion is a Mars technology. It is an excellent Mars technology. It is not an interstellar technology. It does not even flicker in the direction of being an interstellar technology. The rung holds firm for Mars and snaps clean for Alpha Centauri. Move up another rung. Nuclear electric propulsion combines a nuclear reactor with an ion drive. The reactor generates electricity over long periods. That electricity powers an ion thruster, which accelerates charged particles using electric fields and ejects them at extremely high velocities. Ion drives operate on a fundamentally different principle than thermal rockets. Instead of heating gas and letting it expand through a nozzle, they use electromagnetic forces to accelerate individual ions to speeds far exceeding what any thermal process can achieve. The trade-off is thrust. Ion drives produce extraordinarily little force at any given moment, but they produce it continuously for months or years at a time, and the cumulative velocity change can be substantial. NASA's Dawn spacecraft, which orbited both the asteroid Vesta and the dwarf planet Ceres in a single mission, used ion propulsion with a specific impulse of roughly 3,100 seconds. Its 3 xenon ion engines each produced about 90 millinewtons of thrust. 90 millinewtons. That is roughly the force exerted by the weight of a single sheet of printer paper resting on your palm. You would not feel it. A light breeze overwhelms it. Yet this whisper of thrust, applied continuously in the vacuum of space where no friction opposes it, accumulated a total delta V of roughly 11 kilometers per second over the course of the mission. Dawn could not have reached its destinations using chemical rockets without a vehicle many times larger. Ion propulsion made the mission possible by trading thrust for endurance, force for patience. Experimental ion drives in laboratory settings have pushed specific impulse values even higher. Hall effect thrusters and gridded ion engines have demonstrated specific impulses exceeding 10,000 seconds in test chambers. The Variable Specific Impulse Magnetoplasma rocket, known as VASIM, has been tested at specific impulses of roughly 5,000 seconds, with theoretical projections reaching over 10,000. These numbers represent a genuine leap in propulsive efficiency. 10,000 seconds of specific impulse means exhaust velocities roughly 20 times higher than chemical rockets and 10 times higher than nuclear thermal. The fuel mass required for any given velocity change drops dramatically. Ion drives paired with nuclear electric power sources could potentially enable faster Mars transits. Some mission studies suggest that high-power nuclear electric propulsion could reduce Mars transit time to roughly 2 months, a significant improvement over chemical or even nuclear thermal options. For the inner solar system and the asteroid belt, nuclear electric propulsion represents a genuinely transformative technology, but their tortoise-like acceleration makes them impractical for crewed interstellar missions where transit time is the defining constraint. Accelerating a crewed spacecraft massing hundreds of thousands of kilograms to even 1% of light speed using ion propulsion would require continuous thrusting for decades. The nuclear reactor providing the electricity would need to operate at high power output, without a single critical failure, for longer than most nations have existed as political entities. The ion thrusters themselves would need to withstand continuous operation for durations that exceed their demonstrated lifetimes by factors of hundreds. Theoretically conceivable. Practically, the word absurd does not adequately convey the gap between what would be required and what has ever been achieved. Ion propulsion holds firm for Mars. It holds firm for Jupiter and Saturn and the outer planets. It bends dangerously for the Kuiper Belt and the Oort cloud, and it snaps completely for Alpha Centauri. The rung breaks, we climb higher. Now consider the most audacious propulsion concept ever seriously studied by professional engineers and physicists, with security clearances and government funding. Project Orion, conceived at General Atomics in San Diego in the late 1950s, proposed propelling a spacecraft by detonating nuclear bombs behind it. Not small nuclear devices carefully shaped for minimal yield. Full-scale fission or fusion warheads ejected from the aft of the spacecraft and detonated at a rate of roughly 1 explosion per second. A massive pusher plate, mounted to the spacecraft's hull through a system of enormous shock absorbers, would intercept the blast debris and radiation pressure from each detonation and convert it into forward thrust. The spacecraft would ride a continuous sequence of nuclear explosions like a surfer riding a wave made of atomic fire. Project Orion represents the brute force approach to propulsion, and it was studied by some of the most brilliant physicists of the 20th century. Freeman Dyson, one of the greatest theoretical physicists of his generation, worked on the project and later wrote about it with a mixture of scientific enthusiasm and moral unease. The concept works by harnessing the most powerful energy release humanity has ever achieved, nuclear detonation, and channeling it directly into spacecraft acceleration. The energy density of nuclear reactions exceeds chemical reactions by a factor of roughly 1 million. This million-fold advantage translates into specific impulse values that dwarf every other propulsion concept on the ladder. The specific impulse estimates for an Orion-type vehicle range from 6,000 seconds for a conservative fission bomb design to over 100,000 seconds for an optimized fusion pulse variant. The high end of that range exceeds any other propulsion concept that has been studied in engineering detail by an order of magnitude. 100,000 seconds of specific impulse means exhaust velocities approaching 100 kilometers per second, roughly 22 times faster than the best chemical rockets. At these performance levels, the interstellar math begins, for the first time on the ladder, to shift from impossible toward merely extraordinary. An Orion vehicle using fusion bombs could theoretically accelerate to roughly 3 to 5% of the speed of light. At 3%, the journey to Alpha Centauri would take approximately 140 years. At 5%, roughly 85 years, still longer than a current human lifetime but no longer geological. The timeline shrinks from 70,000 years to less than a century and a half. This is the first propulsion concept on the ladder, where Alpha Centauri becomes even theoretically reachable within a time frame that carries meaning. Not within a single human lifetime, perhaps, but within the lifespan of a civilization, within the duration of a long-term institutional commitment, within the kind of time scale that cathedrals and constitutions operate on. But the practical obstacles tower over the theoretical promise. A full-scale interstellar Orion vehicle would need to carry hundreds of thousands of nuclear warheads. The original Orion design studies estimated that an interplanetary version would require roughly 800 bombs. An interstellar version, needing to accelerate to a significant fraction of light speed and then decelerate at the destination, would require a nuclear arsenal dwarfing the combined stockpiles of every nation on Earth. The spacecraft itself would need to be massive, potentially weighing millions of tons, to survive the repeated nuclear blasts without structural failure. The pusher plate alone would need to be fabricated from materials capable of withstanding repeated exposure to nuclear fireball temperatures and pressures, a material science challenge that remains unsolved. The Partial Test Ban Treaty of 1963 explicitly prohibits nuclear detonations in outer space. This treaty, signed by the United States, the Soviet Union, and the United Kingdom, and subsequently ratified by over 100 nations, would need to be renegotiated or abandoned before any Orion-type mission could legally proceed. The environmental consequences of launching millions of tons of nuclear material through Earth's atmosphere, even in a launch vehicle designed to minimize risk, are difficult to overstate. A single launch failure would scatter nuclear warheads across a wide area. The political and diplomatic consequences of announcing an intention to detonate thousands of nuclear weapons in space would reshape international relations overnight. And even if all these obstacles were somehow resolved through unprecedented international cooperation and political will, 85 years of continuous mechanical operation demands reliability standards that no machine in human history has approached. The longest operating human machine is arguably the Voyager spacecraft at roughly 47 years, and it has already lost most of its functionality. An Orion interstellar vehicle would need to maintain structural integrity, navigation capability, and life support for nearly twice that duration under conditions of repeated nuclear blast exposure. The engineering challenge is not merely hard, it may represent a permanent practical barrier even if the physics is sound. Project Orion sits in a peculiar and lonely category in the history of propulsion. It is the only propulsion system ever studied in professional engineering detail that could theoretically reach another star system within a time frame shorter than geological epochs. And it is also completely impractical for reasons that have nothing to do with physics and everything to do with politics, international law, environmental risk, material science, and the sheer audacity of proposing nuclear detonation as a transportation method. The rung holds in theory. It disintegrates in practice. Solar sails deserve a separate rung on the ladder because they represent a propulsion concept fundamentally different from everything below them. Every other system discussed so far carries its energy source on board in the form of chemical propellant, nuclear fuel rods, or ionizable gas. A solar sail carries nothing. It uses the pressure of sunlight itself, photons streaming outward from the sun, striking a reflective surface and imparting momentum through radiation pressure to gradually accelerate a spacecraft. No fuel, no combustion, no exhaust. Just photons bouncing off a mirror. The physics is real and has been demonstrated in space. Japan's Ikaros mission, launched in 2010, became the first spacecraft to successfully demonstrate solar sail propulsion during an interplanetary cruise. The sail measured roughly 14 meters diagonally and was made of a polyimide film only 7.5 micrometers thick, thinner than a human red blood cell. Sunlight pressure accelerated Ikaros by a tiny but measurable amount during its journey toward Venus, confirming that solar sail propulsion works outside a laboratory. The Planetary Society's LightSail 2 mission, deployed in 2019, proved that a solar sail could raise a spacecraft's orbit around Earth using sunlight pressure alone, a controlled demonstration of solar sailing as a practical maneuvering tool. The advantage of solar sails is endurance. Because they carry no fuel, they never run dry. They can accelerate continuously for as long as sunlight reaches them, accumulating velocity over months and years without consuming any onboard resource. This makes them theoretically ideal for long-duration missions where gradual acceleration is acceptable. But the thrust they produce is extraordinarily small, even smaller than ion drives at typical distances from the Sun. At Earth's distance, solar radiation pressure exerts roughly 9 micronewtons per square meter of perfectly reflective sail. For a sail 100 meters on a side, that translates to about 90 millinewtons of total force, comparable to the thrust of an ion engine but acting on a structure that masses far less. The result is meaningful acceleration for lightweight payloads, but the force drops off with the square of the distance from the Sun. By the time a solar sail reaches Jupiter's orbit, roughly 5 astronomical units out, the available radiation pressure has fallen to approximately 4% of its value near Earth. By Saturn's orbit, roughly 1%. Beyond Saturn, sunlight becomes so feeble that the sail is essentially coasting, gaining no further velocity. For interstellar applications, this distance penalty creates a specific strategy. A solar sail aimed at the stars would first dive inward toward the Sun rather than away from it, executing a close perihelion pass at a distance of perhaps 10 to 20 solar radii. At these distances, solar radiation pressure increases enormously, potentially hundreds or thousands of times stronger than at Earth's distance. The sail would gain tremendous velocity during this brief close approach, then swing outward on a hyperbolic trajectory, carrying whatever speed it accumulated during those intense minutes or hours near the Sun. Studies suggest that a highly reflective, ultra-lightweight sail executing a perihelion pass at roughly 10 solar radii, roughly 7 million kilometers from the Sun's surface, could potentially reach velocities of 1 to 2% of the speed of light. At 2%, Alpha Centauri would require roughly 212 years of flight. At 1%, roughly 425 years. Faster than Voyager by orders of magnitude, but still measured in centuries rather than decades. The engineering challenges of the close solar pass are severe. At 10 solar radii, the sail would experience temperatures approaching 1,500 degrees Celsius. Conventional sail materials like polyamide or aluminized mylar would vaporize instantly. The sail would need to be fabricated from refractory materials, perhaps carbon fiber composites or advanced ceramic films, capable of surviving extreme thermal loads while maintaining reflectivity and structural integrity. No such material has been demonstrated at the scale required. The sail would also experience intense ultraviolet and X-ray radiation from the solar corona at close approach, which could degrade or destroy thin film materials in seconds. Solving these thermal and radiation survival problems represents a major open challenge in materials science. A related concept that operates on different physical principles is the magnetic sail, or mag sail. Proposed by Robert Zubrin and Dana Andrews in 1988, the mag sail uses a large superconducting loop of wire, potentially tens of kilometers in diameter, to generate a magnetic field that interacts with the charged particles of the solar wind and, at interstellar velocities, with the thin plasma of the interstellar medium itself. Rather than catching photons like a solar sail, a mag sail catches protons and electrons, deflecting them to produce drag or thrust depending on the relative velocity. The mag sail is particularly interesting not for acceleration but for deceleration. A spacecraft that has been boosted to interstellar speed by some other means, whether laser, fusion or nuclear pulse, faces the problem of slowing down at the destination. Carrying deceleration fuel doubles the mass budget and dramatically worsens the rocket equation. A mag sail could potentially provide braking force by interacting with the interstellar medium, slowing the spacecraft over years or decades without requiring any onboard fuel expenditure. This makes it a complementary technology rather than a standalone propulsion system. It does not solve the acceleration problem, but it could potentially solve the deceleration problem, which is half the interstellar challenge. Solar sails and magnetic sails hold firm for Mars, though they are impractically slow for crewed missions to that destination. They crack for Alpha Centauri but do not entirely shatter. They offer centuries rather than millennia, still too long for human passengers, possibly viable for robotic probes carrying instruments designed for extreme longevity, if the material science of close solar pass survival and superconducting loop deployment advances sufficiently over the coming decades. Each rung of the propulsion ladder reveals the same devastating pattern. The technology works beautifully for Mars. It fails catastrophically for Alpha Centauri. Chemical rockets reach Mars in 7 months. They cannot reach Alpha Centauri in any meaningful time frame. Nuclear thermal propulsion reaches Mars in 4 months. It cannot reach Alpha Centauri either. Ion drives can explore the solar system efficiently over years and decades. They cannot push a crewed spacecraft to interstellar speeds within human timescales. Solar sails can potentially achieve low percentages of light speed, but require centuries of flight time. Only nuclear pulse propulsion, the most extreme and politically untenable concept ever studied, even begins to make the interstellar math work, and it does so only by invoking engineering challenges, legal barriers, and political impossibilities that may be permanently unsolvable. The reason for this pattern is not incremental. It is not that interstellar travel is slightly harder than a Mars mission, or even 10 times harder. The reason is the energy wall. This wall separates planetary travel from stellar travel as absolutely as the sound barrier once separated subsonic from supersonic flight, except the energy wall is vastly more difficult to breach. The sound barrier required only a modest increase in engine power and an understanding of transonic aerodynamics. The energy wall between Mars and Alpha Centauri requires a million-fold increase in energy expenditure and propulsion physics that does not yet exist outside of theoretical papers. Consider the kinetic energy required for interstellar velocities in concrete terms. Kinetic energy equals 1/2 times mass times velocity squared. For a modest spacecraft weighing 100,000 kilograms, roughly the mass of the International Space Station, achieving 10% of light speed requires approximately 4.5 times 10 to the 19th joules of kinetic energy. That is 45 billion joules concentrated in a single object. To contextualize that number, the total annual energy consumption of all human civilization, every nation, every city, every factory, every vehicle, every light bulb, every server farm on the planet, is approximately 5.8 times 10 to the 20th joules. That means accelerating a single International Space Station mass spacecraft to 10% of light speed requires roughly 8% of the total energy humanity produces and consumes in an entire year. All the coal burned in China, all the oil refined in the Middle East, all the natural gas piped across Russia, all the nuclear reactors humming in France, all the solar panels in the American Southwest and the wind turbines in the North Sea, every hydroelectric dam, every geothermal plant, every biomass generator on Earth running for 12 continuous months produces barely enough energy to push one modest spacecraft to 1/10 of the speed of light. And that calculation is generous. It ignores efficiency losses in converting raw energy into directed kinetic energy. Real propulsion systems waste enormous amounts of energy as heat, radiation, and unconverted reaction products. The actual energy input required would be several times higher than the theoretical minimum. It also ignores deceleration at the destination. A spacecraft arriving at Alpha Centauri at 10% of light speed needs to slow down unless the mission is a flyby. Deceleration requires roughly the same energy as acceleration, doubling the total energy budget, and it ignores the mass of the fuel itself. Fuel has mass. That mass must also be accelerated. Carrying fuel to accelerate fuel creates an exponential penalty described by the rocket equation that pushes the actual energy requirement far above the naive kinetic energy calculation. The Mars mission, by contrast, requires kinetic energy measured in roughly 10 to the 13th joules, a large number by everyday standards, equivalent to the energy released by a small nuclear weapon, but achievable with chemical rockets carrying a few hundred tons of propellant. The gap between 10 to the 13th joules for Mars and 10 to the 19th joules for interstellar velocities is a factor of 1 million. Interstellar travel at modest fractions of light speed requires approximately 1 million times more energy than a Mars transfer orbit. 1 million times more. Not double, not 10 times, not 100 times, not 1,000 times. 1 million times more energy to cross the gap between our nearest planetary neighbour and our nearest stellar neighbour. To feel that factor of 1 million in human terms, consider a car driving on a highway. A typical sedan requires roughly 60 kilowatt-hours of energy, the equivalent of about 2 gallons of gasoline, to drive 100 kilometers at highway speed. Now imagine someone tells you that your next trip will require not 2 gallons, but 2 million gallons. That is enough fuel to fill roughly 40 Olympic swimming pools. You would need a convoy of tanker trucks stretching for miles just to carry the gasoline for a single car trip. The car itself would be buried under the weight of its own fuel supply. The trip has not gotten slightly harder. It has transformed into a fundamentally different kind of problem, one where the vehicle you started with is no longer recognizable, and the infrastructure required to support the journey dwarfs the journey itself. That is what the million-fold energy gap between Mars and Alpha Centauri means in practice. It does not scale up the existing problem. It replaces the existing problem with something categorically new. This is the energy wall. It is not a fence you can climb with better engineering or more efficient nozzle designs. It is not a hill you can summit with incremental improvements in fuel chemistry. It is a cliff face, sheer and vertical, that demands an entirely different relationship with energy production and propulsion physics. Chemical rockets cannot scale to meet it. Nuclear thermal cannot. Ion drives cannot. Solar sails cannot. Only concepts that harness the full energy of nuclear detonation, or physics that humanity has not yet mastered, even approach the energy scale required. The propulsion ladder that carries us confidently and competently to Mars shatters beneath our feet the moment we aim for the stars. Every rung we have built breaks. Every rung we have designed on paper breaks. Every rung we have theorized in physics journals breaks or bends so severely that the practical challenges become indistinguishable from impossibility. Mars sits comfortably within the reach of technologies we possess today. Alpha Centauri sits beyond the reach of every technology we have ever seriously engineered. The wall between them is not made of distance alone. Distance is just the symptom. The wall is made of energy. It is made of the fundamental relationship between mass, velocity, and the joules required to connect them. It is made of the rocket equation's exponential penalty and the finite energy density of every fuel source humanity has ever harnessed. It is a wall that no incremental advance in engineering can breach, because the problem is not engineering, the problem is physics, and understanding what could conceivably breach that wall, what discoveries and inventions and breakthroughs might someday transform Alpha Centauri from a theoretical impossibility into a practical destination, requires leaving the solid ground of proven technology and designed hardware entirely. It requires stepping into the realm of physics we do not yet possess, energy sources we cannot yet harness, and propulsion concepts that exist today only as equations on a whiteboard and dreams in the minds of physicists who understand exactly how far those equations are from becoming real machines. The gap between Mars and Alpha Centauri is not waiting to be closed by incremental progress. It will not yield to faster computers, lighter materials, better manufacturing processes, or more generous funding cycles. The previous section demonstrated that every propulsion technology humanity has built or seriously designed fails against the interstellar distance. Chemical rockets, nuclear thermal engines, ion drives, solar sails, even nuclear pulse propulsion, each one either shatters against the energy wall or demands practical compromises so extreme they become indistinguishable from impossibility. Closing the gap between our nearest planet and our nearest star requires something qualitatively different. It requires breakthroughs in fundamental physics, the kind that rewrite textbooks, overturn assumptions, and redefine what human civilization can achieve. Understanding what those breakthroughs would look like, how close or far we stand from them, and what they would demand of our species reveals the true depth of the chasm between interplanetary ambition and interstellar reality. The first candidate is fusion propulsion. Nuclear fusion is the process that powers every star in the observable universe. Deep within the sun's core, where temperatures exceed 15 million degrees Celsius and pressures crush matter to densities 13 times that of lead, hydrogen nuclei are forced close enough together for the strong nuclear force to overcome their electromagnetic repulsion. They fuse into helium. In doing so, they convert roughly 0.7% of their combined mass directly into energy. This conversion ratio sounds small until you apply Einstein's equation relating energy to mass multiplied by the speed of light squared. The speed of light squared is an enormous number, approximately 9 times 10 to the 16th in metric units. Even 0.7% of a kilogram, run through that equation, releases energy equivalent to roughly 630 billion joules. That is roughly 1 million times more energy per kilogram than the best chemical propellants can deliver. Fusion does not merely improve upon chemical combustion, it operates in an entirely different energy regime. A fusion rocket would exploit this million-fold advantage by heating propellant to temperatures far beyond what any chemical flame or fission reactor can achieve. The superheated exhaust would exit the engine at velocities measured in hundreds or thousands of kilometers per second, rather than the single-digit kilometers per second that chemical nozzles produce. Theoretical specific impulse values for fusion propulsion range from 10,000 seconds on the conservative end, using designs that capture only a fraction of the fusion energy, to over 1 million seconds for advanced concepts that efficiently convert fusion plasma into directed thrust. At the high end of that range, a fusion rocket could theoretically accelerate a spacecraft to roughly 10% of the speed of light. At 10% of light speed, roughly 30,000 kilometers per second, the journey to Alpha Centauri would take approximately 43 years. 43 years. A number that fits inside a single human lifetime, a number that transforms interstellar travel from a geological abstraction into something resembling a long but conceivable career-length mission. This is the promise that has kept fusion propulsion in the scientific conversation for over half a century, and it is precisely why some of the most detailed interstellar mission studies ever conducted have centered on fusion as the enabling technology. The British Interplanetary Society's Project Daedalus, conducted between 1973 and 1978, remains one of the most rigorous interstellar mission designs ever produced. A team of volunteer engineers and scientists designed an unmanned probe that would reach Barnard's star, a red dwarf approximately 6 light-years away, within a 50-year flight time. The propulsion system relied on inertial confinement fusion. Pellets of deuterium and helium-3, each roughly the size of a marble, would be injected into a combustion chamber at a rate of 250 per second. Powerful electron beams would compress each pellet to the point of fusion ignition. The resulting micro-explosions would produce plasma exhaust at tremendous velocity, accelerating the spacecraft to roughly 12% of light speed over a boost phase lasting approximately 2 years. The Daedalus design was enormous. The complete vehicle massed approximately 54,000 tons at departure, most of which was fuel. The first stage alone carried roughly 46,000 tons of deuterium and helium-3 pellets. The second stage carried an additional 4,000 tons. The payload, the actual scientific instruments that would study Barnard's star during a high-speed flyby, weighed roughly 450 tons. The mass ratio was extreme, but not physically impossible. The physics checked out. The engineering, however, exceeded anything humanity could build in the 1970s, and it still exceeds anything humanity can build today. The fundamental obstacle is not the spacecraft design, it is the engine. No laboratory on Earth has achieved sustained, controlled, net positive nuclear fusion. The word sustained is critical. The National Ignition Facility at Lawrence Livermore National Laboratory achieved a landmark result in December 2022 when it produced fusion ignition, a condition where the energy released by fusion reactions exceeded the energy delivered to the fuel target by the facility's laser array. The lasers delivered roughly 2.05 megajoules to the target. The fusion reactions produced roughly 3.15 megajoules, a net gain of roughly 50%. This was genuinely historic. It demonstrated that the physics of inertial confinement fusion works as predicted. But the context is sobering. The laser system that delivered those 2 megajoules to the target consumed roughly 300 megajoules of electricity from the grid. The overall system efficiency, from wall plug to fusion energy output, was roughly 1%. The reaction lasted a few billionths of a second. It was not sustained. It was not repeated continuously. It produced enough energy to boil roughly 10 kettles of water. Building a power plant, let alone a Starship engine, from this achievement requires improvements in efficiency, repetition rate, and energy capture that span orders of magnitude. The International ITER project, currently under construction in Cadarache in southern France, represents humanity's largest bet on the alternative approach to fusion, magnetic confinement. ITER uses superconducting magnets to confine a plasma of deuterium and tritium at temperatures exceeding 150 million degrees Celsius, roughly 10 times hotter than the core of the Sun. The project aims to produce 10 times more fusion power than the heating power injected into the plasma, a milestone called Q equals 10. First plasma is projected for the late 2020s, with full deuterium-tritium fusion experiments beginning in the mid-2030s. Even if ITER achieves its goals on schedule, which no major fusion project in history has done, it will demonstrate scientific feasibility, not engineering readiness. A commercial fusion power plant based on ITER's design is decades beyond that. A fusion engine compact enough, reliable enough, and powerful enough to propel a spacecraft to interstellar velocities is decades beyond the power plant. The timeline compresses into a familiar and frustrating joke within the physics community. Fusion has been 20 years away for the past 60 years. This is not because the physicists working on it are incompetent or lazy. It is because confining a plasma at 150 million degrees, sustaining the conditions for continuous fusion reactions, and extracting net energy from the process while preventing the plasma from touching any physical wall and instantly cooling, is one of the hardest engineering problems humans have ever attempted. Plasma is wildly unstable. It writhes and twists against magnetic confinement. It develops instabilities with names like kink modes and ballooning modes, and edge-localized modes that can dump enormous amounts of energy onto reactor walls in milliseconds. Controlling these instabilities requires real-time feedback systems of extraordinary precision, operating in an environment of extreme temperature, intense neutron radiation, and powerful magnetic fields. The Sun accomplishes fusion effortlessly because it confines its plasma with 330,000 Earth masses of gravitational pressure. Spacecraft cannot carry a star's worth of gravitational confinement in their engine bay. Fusion propulsion for interstellar travel requires not merely achieving fusion on the ground, but miniaturizing a reactor into something that fits aboard a spacecraft, making it reliable across decades of continuous uninterrupted operation in the vacuum of space with no maintenance crew, and scaling it to power levels that dwarf any terrestrial fusion reactor yet designed. A Daedalus-class engine would need to ignite 250 fusion micro-explosions per second for 2 continuous years during the acceleration phase. That is roughly 15.8 billion successive fusion ignitions without a single misfire catastrophic enough to damage the engine. Each step in this chain, ground-based fusion, compact reactor, space-rated engine, interstellar-scale power output, represents a frontier that could take decades to cross. Together, they place practical fusion-powered starships somewhere between several decades and several centuries in the future. Nobody knows which end of that range is correct. The honest answer is that the timeline depends on discoveries that have not yet been made. The second candidate occupies the extreme upper end of the energy density spectrum. Antimatter is the most energy-dense substance known to physics. Every particle of ordinary matter has a corresponding antiparticle with identical mass but opposite charge. When a particle meets its antiparticle, both are annihilated, and their entire combined mass is converted into energy. Not 0.7%, as in fusion. Not 0.1%, as in fission. 100%, total conversion. Every last fraction of a kilogram becomes energy, according to Einstein's equation, with nothing left over. 1 gram of antimatter, meeting 1 gram of normal matter, releases approximately 1.8 times 10 to the 14th joules of energy. To make that number tangible, it is roughly equivalent to the energy released by the nuclear weapon that destroyed Hiroshima from 2 grams of material, a weight you would not notice if someone placed it in your palm. The energy density of antimatter exceeds chemical propellants by a factor of roughly 10 billion. It exceeds nuclear fission by a factor of roughly 1,000. It exceeds nuclear fusion by a factor of roughly 140. No other energy source in known physics comes close. A spacecraft carrying just a few tens of kilograms of antimatter could theoretically accelerate to significant fractions of light speed. Various design concepts have been proposed. Some envision pure antimatter rockets where antihydrogen annihilates with hydrogen, producing pions and gamma rays that are magnetically directed to produce thrust. Others propose antimatter-catalyzed fusion, where tiny quantities of antimatter are used to trigger fusion reactions in a much larger supply of conventional fusion fuel, combining antimatter's ignition capability with fusion fuel's relative abundance. Still others propose antimatter-heated propellant schemes, where annihilation energy heats a working fluid that is then expelled through a nozzle, sacrificing some efficiency for engineering simplicity. The physics behind every one of these concepts is impeccable. Antimatter annihilation is among the best understood processes in particle physics. The equations are exact. The energy yields are precisely calculable. There is no theoretical uncertainty about whether antimatter propulsion would work. It would work spectacularly. The problem is not physics. The problem is manufacturing. The entire annual output of every particle accelerator on Earth, including CERN's Large Hadron Collider, Fermilab's facilities, and every other high-energy physics laboratory on the planet, produces roughly 1 to 10 nanograms of antimatter per year. 1 nanogram is 1 billionth of a gram. To manufacture a single gram of antimatter at current production rates would require approximately 1 billion years. The timeline exceeds the remaining lifespan of the Sun. It exceeds the age of complex life on Earth. Producing the tens of kilograms needed for an interstellar mission at current rates would require a duration that dwarfs the age of the universe itself. The energy cost is equally prohibitive. Producing antimatter requires creating particle-antiparticle pairs, using high-energy collisions in particle accelerators. The process is inherently inefficient because most of the collision energy goes into forms other than antimatter production. Current technology converts roughly 1/10 billionth of the input energy into antimatter rest mass energy. Producing 1 gram of antimatter at this efficiency requires approximately 25 million billion kilowatt-hours of electrical energy. The total annual electricity production of every power plant on Earth is roughly 28 trillion kilowatt-hours. Manufacturing a single gram of antimatter would therefore consume roughly 1 million times the world's total annual electricity output, 1 gram. A quantity you could lose between your couch cushions. These production barriers are not temporary limitations awaiting a clever engineering fix. They reflect fundamental aspects of how particle physics works. Antiparticles are created in pairs with normal particles, requiring at minimum the rest mass energy of both particles as input. The collider infrastructure needed to produce antimatter at useful rates, even with revolutionary efficiency improvements, would require energy inputs on a civilizational scale that humanity does not currently possess and will not possess for generations. Some physicists have speculated about harvesting naturally occurring antimatter from cosmic ray interactions in planetary magnetospheres, or discovering dense concentrations of antimatter somewhere in the galaxy. These remain speculative ideas without supporting evidence. Antimatter propulsion sits in the most tantalizing and frustrating category of space technology. The physics is perfect. The energy density is unmatched by any known substance. The theoretical performance would solve the interstellar problem outright. And the practical barriers to producing the fuel are so extreme that they may require the construction of Dyson spheres, megastructures that capture the entire energy output of a star, or equivalent civilizational scale energy infrastructure, before antimatter becomes available in useful quantities. We can write the equations for an antimatter starship today. We cannot fill its fuel tank in any century visible from where we stand. The third candidate takes a radically different approach to the energy problem. Rather than trying to carry enough fuel aboard the spacecraft, it leaves the energy source behind on the ground. Breakthrough Starshot, publicly announced in 2016 with $100 million in initial funding from billionaire investor Yuri Milner and the enthusiastic endorsement of the late Stephen Hawking, proposes using a ground-based laser array to accelerate gram-scale probes to approximately 20% of the speed of light. The concept is elegant in its simplicity. A phased array of thousands of individual lasers, synchronized to produce a single coherent beam, would be constructed on Earth's surface, likely at a high-altitude site to minimize atmospheric interference. The combined output of this array would reach roughly 100 gigawatts, comparable to the total electricity consumption of a mid-sized nation. This beam would be focused on a reflective sail, approximately 4 meters in diameter and weighing less than a gram per square meter, attached to a probe called a Starship, weighing roughly 1 to 4 grams. The sail would be composed of an advanced metamaterial engineered to reflect the laser wavelength with extreme efficiency while surviving the intense radiation pressure and heating. The laser would fire for approximately 10 minutes. During that time, the tiny probe would accelerate at roughly 10,000 times the force of Earth's gravity. By the time the laser switched off, the probe would be traveling at roughly 60,000 kilometers per second, 20% of the speed of light. No onboard fuel, no engine, no exhaust. Just a beam of light pushing a mirror through the vacuum of space. At 20% of light speed, the probe would reach the Alpha Centauri system in roughly 21 years. It would tear through the system at tremendous velocity, far too fast to enter orbit or land on anything. The flyby would last seconds, perhaps minutes at most. During that brief window, onboard cameras and sensors, etched onto a silicon chip weighing milligrams, would capture images and data about any planets in the system. The probe would then transmit this data back to Earth using a tiny onboard laser, with the return signal requiring another 4.24 years to cross interstellar space at the speed of light. Total mission time from laser firing to data reception on Earth, roughly 25 years. A single human generation. Breakthrough Starshot is currently the most credible near-term interstellar mission concept in existence. The physics of radiation pressure acceleration is well established and experimentally verified. No new laws of nature are required. The engineering challenges are extreme, but do not violate known physics. Building a 100 gigawatt coherent laser array is beyond current capability, but represents an extension of existing technology rather than a departure from it. Fabricating a sail material that reflects efficiently without melting under 100 gigawatts of focused laser radiation is an open materials science problem but not a thermodynamic impossibility. Navigating a gram-scale probe across 4 light-years of interstellar space with no course correction capability requires extraordinary precision in the initial laser aiming, but is calculable within known physics. Yet each of these challenges, when examined closely, reveals layers of difficulty that illustrate why even the most promising interstellar concept demands decades of development. The sail heating problem is perhaps the most immediate. 100 gigawatts of laser power focused on a 4-meter sail means roughly 8 gigawatts per square meter of incident radiation during the boost phase. For comparison, the surface of the Sun delivers roughly 64 megawatts per square meter. The Starshot sail would experience radiation intensity roughly 125 times greater than the surface of the Sun for 10 continuous minutes. Any imperfection in the sail's reflectivity, any microscopic region that absorbs rather than reflects, would become a hotspot that could vaporize the sail material in milliseconds. The sail must reflect at least 99.99% of the incoming laser light to survive. Current laboratory mirrors achieve this reflectivity only for specific wavelengths under controlled conditions. Fabricating a sail that maintains this performance while weighing less than a gram per square meter, surviving the mechanical stress of 10,000 gravity acceleration, and remaining stable against beam-riding perturbations is an open problem in metamaterial engineering that no laboratory has yet solved. Beam-riding stability presents its own challenge. A flat reflective sail being pushed by a laser beam is inherently unstable, like balancing a ball on the tip of a pencil. Any slight tilt of the sail relative to the beam axis creates an asymmetric force that pushes the sail further off-center, leading to rapid loss of alignment and mission failure. Proposed solutions include shaping the sail into a slightly concave or conical geometry that creates a restoring force, similar to how a parachute self-stabilizes in an airstream. But the dynamics of a relativistically accelerating sail under gigawatt-scale laser illumination have never been tested experimentally. The tolerances are measured in fractions of a degree, maintained over 10 minutes of continuous acceleration at forces that would crush any human flat. Finally, the communication challenge may be the most underappreciated. A Starship probe weighing a few grams cannot carry a large antenna or a powerful transmitter. It must beam data back to Earth across 4.24 light-years, using a laser that weighs milligrams and produces milliwatts of power. The signal arriving at Earth would be extraordinarily faint, requiring a receiving array of enormous size and sensitivity. Current plans envision using the same ground-based laser array that launched the probe, now repurposed as a receiver, to detect the returning signal. Even so, the data rate would be measured in bits per second, not megabits. Transmitting a single high-resolution image of a planet orbiting Proxima Centauri could take days or weeks. The probe would need to store its data on board and transmit continuously for months after the flyby, all using electronics that survived 10,000 gravity acceleration and 21 years of interstellar radiation exposure with no shielding. Every one of these sub-problems is solvable in principle. None of them has been solved in practice. The critical limitation is what Breakthrough Starship cannot do. It cannot carry humans. The probes weigh grams, a few grams. They carry no life support, no crew cabin, no food, water, or air. No radiation shielding, no deceleration system. They are cameras on a beam of light, traveling one way at 60,000 kilometers per second, passing through the Alpha Centauri system like a bullet passing through a room. They photograph what they can in the seconds available and transmit what they captured before vanishing into the interstellar void forever. Scaling the concept to carry a crewed vehicle transforms the engineering from challenging to essentially impossible with foreseeable technology. A crewed spacecraft massing even 10,000 kilograms, a tiny vehicle by any standard, would require a laser array roughly 1 billion times more powerful than the Starship design to achieve the same acceleration. 100 gigawatts becomes 100 exawatts, a power level that exceeds the total energy output of the Sun, intercepted by Earth by a factor of roughly 600. And even if such an array could somehow be built and powered, the crewed vehicle would need a way to decelerate at Alpha Centauri. A laser beam from Earth cannot slow you down at the destination. You would need onboard fuel for braking, which reintroduces the mass problem, which reintroduces the rocket equation, which reintroduces the energy wall that the laser concept was designed to circumvent. Breakthrough Starship is a flyby mission for robotic probes. It could deliver the first close-up images of an exoplanet orbiting another star, a scientific achievement that would rank among the greatest in human history. But it does not solve the problem of sending human beings to the stars. It photographs the destination. It does not deliver passengers. This is where the honest assessment must land. Every credible path to interstellar travel, whether through fusion, antimatter, nuclear pulse, or laser sail, either cannot carry humans, cannot be built with current technology, cannot be fueled with current production capacity, or cannot be operated with current reliability standards. Some of these barriers may fall within decades. Fusion may be achieved commercially by mid-century. Laser technology may advance enough to make Breakthrough Starship feasible within a generation. But the barriers separating robotic flyby probes from crewed interstellar vehicles are not the same barriers separating chemical rockets from nuclear engines. They are barriers of a fundamentally higher order. They require not just better engineering, but new relationships with energy production, new materials, new propulsion physics, and possibly new science that has not yet been conceived. Mars represents an engineering challenge. The physics is solved, the chemistry is understood, The trajectories are calculated to precision. What remains is building the hardware, funding the program, managing the risk, and committing the institutional patience to see it through. These are hard problems, but they are problems that respond to human effort applied within known physical law. More money buys bigger rockets. More testing produces more reliable systems. More time allows technology to mature. Mars bends to will. It yields to persistence. It is a mountain that can be climbed with tools that already exist. Alpha Centauri represents a physics-scale challenge. The energy requirements exceed anything humanity currently produces by factors of millions. The propulsion technologies that could theoretically reach interstellar speeds either do not yet function at any scale, cannot be produced in useful quantities with the energy infrastructure of an entire civilization, or demand operational reliability across timescales that exceed every machine ever built by orders of magnitude. These are not problems that yield to funding alone, no matter how generous. They require discoveries that have not yet been made. They require physics that may not yet have been imagined. The difference between these two categories of challenge is not incremental. It is not the difference between a difficult hike and a very difficult hike, where more preparation and better equipment bridge the gap. It is more like the difference between swimming across a river and swimming across the Atlantic Ocean. One requires endurance and technique within normal human physical limits. The other requires a transformation so fundamental that the word swimming no longer applies. You need a different vehicle, a different energy source, a different relationship with the medium you are crossing. And here is what the gap between Mars and Alpha Centauri ultimately reveals about our place in the cosmos. The solar system feels enormous from Earth's surface. The moon sits 250,000 miles away, far enough that only 24 human beings have ever crossed the distance. Mars is hundreds of millions of kilometers distant, a journey of 7 months that no human has yet attempted. Jupiter is farther still. Saturn, Uranus, Neptune, Pluto, the Kuiper Belt, the Oort cloud. Each successive destination extends the map further into the cold, dark reaches of the Sun's gravitational domain. Voyager 1, after nearly 50 years of flight at 61,000 kilometers per hour, has barely crossed into interstellar space, roughly 24 billion kilometers from home. Yet the nearest star is 40 trillion kilometers away. Voyager has covered less than 0.1% of that distance in half a century. The entire solar system, every planet, every moon, every asteroid, every comet, every spacecraft humanity has ever launched, fits inside a bubble so small compared to the interstellar void that it essentially rounds to zero. We live in a cosmic neighborhood that feels vast, but is actually minuscule. The solar system is not a continent to be explored. It is a single house on a street where the next house sits on the far side of an ocean. Mars is a room in that house. Jupiter is the back garden. The Oort cloud is the property fence. Alpha Centauri is a house in a different city, separated from us by a distance that no vehicle in our driveway can cross. This realization should not create hopelessness. It should not produce despair or nihilistic resignation about humanity's cosmic prospects. What it should create is awe. Genuine, humbling, spine-straightening awe at the scale of the universe and the depth of the challenge it presents. The same species that learn to split atoms, land robots on distant worlds, and decode the structure of space-time itself, stands at the edge of an ocean so wide that crossing it demands physics we have not yet discovered. That is not a failure of imagination. It is an invitation to imagine harder. Every great breakthrough in human history began with confronting a barrier that seemed absolute. The sound barrier was declared unbreakable by serious engineers until Chuck Yeager broke it in 1947. Orbit was physically unreachable until Sputnik reached it in 1957. The moon was an untouchable celestial object, visible but forever beyond human hands, until Neil Armstrong pressed a bootprint into its surface in 1969. Each of these barriers, in its time, looked as permanent and non-negotiable as the interstellar energy wall looks today. Each one fell to a combination of new physics, new engineering, and the stubborn refusal of human beings to accept permanent limitations. Alpha Centauri is the next barrier. It is the greatest one our species has ever faced. It may not fall within this century. It may not fall within the next. It may require discoveries in physics as revolutionary as Einstein's relativity, or as unexpected as quantum mechanics. It may require energy infrastructure on a scale that makes current civilization look like a campfire compared to a power grid. It may require propulsion concepts that no human mind has yet conceived. But Mars will be reached. Within this century, almost certainly within the next 2 decades, human beings will stand on the surface of another planet and look up at an alien sky tinged salmon pink by iron oxide dust. That achievement will mark humanity's transformation from a single planet species into a multi-planet one. It will be celebrated across the world, and rightly so, as one of the defining accomplishments of our civilization. But it will also illuminate, with harsh and beautiful clarity, just how small a step it represents on the cosmic scale. Mars is 1/4 of a light-hour away. Alpha Centauri is 4¼ light-years away. The ratio between them is not a slope, it is a cliff. The distance from Earth to Mars is an engineering problem with a solution that bends to human effort, human funding, and human will. The distance from Earth to Alpha Centauri is a physics problem, whose solution depends on breakthroughs that cannot be scheduled, cannot be purchased, and cannot be willed into existence by ambition alone. The gap between those two truths is measured not in kilometers or light years, but in the difference between what engineering can achieve within known physics and what physics itself must reveal before engineering can begin. That difference is the most humbling number in all of science. Not because it tells us we are small, though it does. Not because it tells us we are insignificant, because it does not. It is humbling because it shows us, with mathematical precision, exactly how much larger the universe is than anything we have yet dared to build. It reveals the solar system, that vast territory we are only now beginning to explore, as a single small room in a mansion of incomprehensible size. It places our greatest engineering achievements, our most powerful rockets, our most ambitious missions, inside a context where they register as the first tentative steps of a species that has only just learned to walk. Mars is within reach, Alpha Centauri is not, and the space between those two facts contains everything humanity still has to discover about the universe, about physics, and about itself.